All right, so let's talk about radicals. This is a new type of mechanism that we haven't discussed previously. Everything else that we've discussed to this point has been neatly classified as a polar mechanism. And really, the difference is in a polar mechanism, bond cleavage is heterolytic, bond making is heterolytic, whereas in radicals, it's one electron at a time. And let me illustrate what I'm talking about. We saw in a previous mechanism how an alkene reacts with HBr. And so two electrons remove a hydrogen, which gives up its two electrons to bromine. This is known as heterolytic bond dissociation or bond cleavage. It produces two ions because, as we've previously seen, we get a positively charged carbocation and we get a negatively charged bromide ion. This is the hallmark of a polar reaction mechanism. Heterolytic bond dissociation. In a radical, however, we would have homolytic bond dissociation. We would have one electron goes to hydrogen, one electron goes to bromine. Notice how the arrows are drawn. You still have the tail of the arrow for the origin of the electrons. Head goes to where the electron is going. But here, there's only a one-sided head. That means only one electron is moving. And so this is called homolytic bond dissociation or heterolytic bond cleavage. This will produce two radicals. In this case, an H radical and a Br radical, both of which are very reactive and will seek to make bonds with new electrophiles. Before we get into actual formal mechanisms, I'd like to go through the patterns of radical electron pushing. Patterns of radical electron pushing. This is going to be analogous to our four mechanistic patterns that we saw with polar reactions, but these are all going to be radicals. So the first one we've already seen. Homolytic bond cleavage. This is almost always the first step of any radical mechanism, and it is called an initiation step. And I think it's wise to discuss what makes it an initiation step. The radical is a product only. meaning that a non-radical reactant like HX usually is irradiated with an energy source like a photon of light, and I get two radical products. This is what makes a mechanistic step in radical reactions an initiation step. A non-radical reactant produces radical products. There are also steps which are radicals as both reactants and products. So propagation is a pattern in which that's kind of an ugly box. Let's fix that. So propagation is where radicals are reactants. So I may have radical A, and it's going to be converted to a different radical, like radical B. Let's look at some examples of this. For example, let's say that I already have a radical that we call an initiator. And I have a carbon molecule. And the new carbon radical that I make is different from the initiator that I had in the beginning of the reaction. This mechanistic pattern is known as hydrogen abstraction. I know you're going to feel tempted to call this a proton transfer, but it's not a proton transfer because you are removing a hydrogen atom plus one electron, not simply a naked proton. So this is hydrogen abstraction. This is not the only type of propagation step that we see in radical mechanisms. So let's look at some others. We can have a carbon radical react with a halogen. This process is called, appropriately enough, halogen abstraction. This allows, in this particular case, a carbon halide bond to be formed, and it produces a new halide radical. This is a propagation step. I had a carbon radical in reactants, and now I have a halide radical in products. Halogen abstraction. Also in propagation, we can add a radical to a pi bond. Now this is setting us up to talk about a very different way of adding HBr to a carbon-carbon double bond. So let's look at having a halide radical having a double bond, and this is a very regiospecific reaction because radicals follow essentially the same kind of energetic stability series that a carbocation does. In other words, tertiaries are more stable than secondaries, are more stable than primaries, are more stable than methyls. The degrees are not as pronounced. Allylics are more stable because of resonance. Benzylics are even more stable, again, because of resonance. And so the new carbon radical that I've made is a secondary radical, which is why the halide is going to add to carbon 1 and not to carbon 2. By the way, if this were HBr adding to this alkene, I would produce the more stable carbocation intermediate. Now, I want you to notice the subtle difference in mechanism here. We're going to get two different products because the first step in the radical reaction adds the halogen to make a more stable radical. But when we react it with an electrophile like HBr, the first atom that's added is a hydrogen to yield a more stable carbocation. The radical will eventually be replaced with, you guessed it, a hydrogen atom. And in the carbocation, it's going to be replaced with, you guessed it, a bromide atom, or bromide ion. Notice the regiochemistry is exactly opposite. A radical reaction with HBr would give you anti-Markovnikov regiochemistry. But if I use HBr without an initiator, like a peroxide, then I would get Markovnikov regiochemistry. I will post a separate video where I go through both of these mechanisms in their entirety to explain this difference. So far in propagation, we've seen a hydrogen abstraction, we've seen a halogen abstraction, we've seen addition of a radical to a pi bond. Now we could also do the opposite of this. We could eliminate a halogen from a pi bond. So let's start with the process that we just finished discussing. This mechanistic process is simply elimination. It's again a bona fide propagation step because I'm converting a carbon radical now into a halide radical. And notice that it is exactly the reverse of the previous process that I described. Here I am adding a halide radical to a pi bond to make a carbon radical. Here I am eliminating a halide from a carbon radical to make a halide radical. So there are four propagation mechanistic patterns: abstraction of a hydrogen, abstraction of a halide, addition, and elimination. This leaves us our only termination step. In a termination step, we're doing the reverse of the initiation. So in the initiation, we didn't have a radical reactant, but it produced a radical product. Here we're going to take two radical products and make two radical reactants and make a single non-radical product. And this is called coupling. For those of you who are single right now, you have your own lone electron. When you decide that you're going to spend whatever amount of time you are with your significant other, you are coupled. You become a couple. So if I have X radical and I have R radical, just as one example, I now become Rx. And boys, that lone electron you used to have is no longer yours. That means your bank account, your possessions, everything you own, your misery, etc. This is coupling. Radical reactants making a non-radical product. This is a termination step. This is a termination step. So radical mechanisms have three steps: an initiation, a propagation, and a termination. What I want to do now is go through how we can convert an alkane to an alkyl halide, stringing together many of these mechanistic steps. So in the model reaction, I'm going to use an alkane that is asymmetrical. I am going to react this alkane with Cl2 in the presence of light. The major product, and this is because tertiary hydrogens are typically replaced more easily because they make more stable radicals. This is what I want to make. Now we're going to have to talk about the inherent difficulties of making this from chlorine versus making this from bromine, but I'll probably save that for another video. Let's look at how I can account for the formation of this product. So of course I need to start with an initiation step. Initiation is easily facilitated because a chlorine-chlorine single bond has a bond dissociation energy of about 58 kJ per mole. In other words, it's not very stable. In the initiation step, a Cl-Cl bond will undergo homolytic bond dissociation in the presence of a photon of light to produce two Cl radicals. This is homolytic bond dissociation, just as we discussed before. Let's look at step 2. One of these Cl radicals is going to react with a tertiary hydrogen in our carbon substrate. Again, this is going to be an abstraction of a hydrogen. And of course, I will get an HCl byproduct. And this mechanistic pattern is hydrogen abstraction. This, of course, is a propagation step, so let's make sure we label that. So we got initiation, we got propagation. Now we have other propagation steps So we're going to start with this carbon radical. And now we're going to perform another mechanistic step we just discussed, which is halogen abstraction. Notice all of these bonds break and make homolytically. One electron from each source. That one arrow is kind of sloppy, so let me straighten this up. Now, this accounts for our major product in the mechanism. We also produce a Cl radical. Let's look at what we have to this point. I've used Cl2 to make two Cl radicals. But I used one of the Cl radicals, but then I later produced another Cl radical. So I still have two Cl radicals that are left. I produced a carbon radical, but I used a carbon radical. Let's just do a termination step where the two Cl radicals that I have built up in solution according to this mechanism now react and yield Cl2. Now, we can take one of my Cl2s and one of these Cl2s, one's a reactant, one's a product, they cancel. The carbon radical cancels. The Cl radicals, I've got 1, 2, 3 in products. I've got 1, 2, 3 in reactants. What am I left with? I'm left with my carbon compound, which was 2-methylbutane. I'm also left with a Cl2, and I have an HCl and a chloroalkane as a product. So this is a pretty complete mechanistic treatment of this process. Now, one thing we do need to discuss is the selectivity of chlorine and bromine. For example, if I go back to this compound, and I start labeling all the hydrogens, I'm going to call these HA. It's almost like going through and doing proton environments for NMR in a sense. If I replace any of the hydrogens of HA with a chlorine, I'll get one particular product. So there are 6 hydrogens in this molecule that are equivalent. And so if I were to replace HA, I would get one product. If I were to replace HB, I get a different product. I'm going to show that with a different color. HC, there's 2 of those. And of course HD, there's 3 of those. So if I ignore all dichlorination and trichlorination, if I'm only considering monochlorination products, I can make 4 products here. Let's draw those. Here's one compound, and there are 6 hydrogens that I can remove to make this compound. I could also, of course this is the one that we showed mechanistically. There's only one hydrogen I can remove to form the tertiary chloro product. Yet another unique product. And we're ignoring stereoisomers, of course, would be this one. And there are 2 hydrogens that I could remove. Finally, even though this has 3 and it's a methyl and these are methyls, they're not the same. They have different names. So if we're just looking at statistical probabilities, I should expect to make this one most often, because I have, in the case of this molecule, twice as many hydrogens. In the case of this molecule, 3 times as many hydrogens. In the case of this one, 6 times as many hydrogens. But there is a radical stability. Tertiary is more stable than secondary, is more stable than primary. When I chlorinate, there's a selectivity rule. And the chlorination selectivity rule is that primary to secondary to tertiary is 1 to 3.8 to 5. What that means is mathematically, I go back, all these primaries I multiply by 1. That's a total of 6. This 3 I multiply by 1. That's a total of 3. These 2 I multiply by 3.8. That's a total of 7.6. And of course this one is tertiary. I multiply by 5. That's a total of 5. If I want to find the relative percents, for example, the one that I made would be 5 over the sum of all of these. So you got 9, 14, 21.6. And then I'll just multiply that by 100%. Don't get a whole lot of this when I chlorinate. Chlorination's fast, but it's not selective. The other way that we halogenate is bromination. Bromination, primary to secondary to tertiary, is 1 to 82 to 1600. Let's look at the same products again, only now let's look at bromination. To do this, I'll need one more palette. So, let's see. Again, there are 6 positions for this, but each one has a relative stability of 1. So this allows me to take into consideration radical stability and statistical availability of hydrogens to abstract. Both of those are important. And really, they're both equally weighted. This will be 3 times 1, or 3. This will be 2 times 82, or 164. This is 1 times 1600. 1600. That means that this tertiary product, 1600 over 1773 times 100%. That is by far and away the major product, not even close. So bromination, much slower kinetically, but gives you a much more selective process in terms of making either a secondary or a tertiary alkyl bromide. So in the lab, if we use the free radical mechanism, we do bromination over chlorination. So on the next video, I want to post the difference in the mechanism between reacting HBr with an alkene and then reacting HBr with a peroxide initiator. And we'll see that the difference is one of regioselectivity.